Okay, let's continue. So today I'll basically try to give a big recap of whatever we have seen in this course so far, and probably towards the end of the class I'll discuss about stabilizing 3-stage and 4-stage OTAs, but nothing more than that. Typically I don't like to take classes during the mid-semester week, but because I lost classes in the last week I had to do it. So yeah. So again, so if you were to start from the beginning, so remember we started with the goal of making an op-amp, and the op-amp is a block that takes difference between two signals, amplifies it by a large gain. And why do we need an op-amp with a large gain? So that we can use it in negative feedback, and the only active or incrementally active device we had was a transistor. So like a kid who was given a toy, we decided to give inputs at different place and try to see what happens at different ports. So that gave rise to the common configurations, the common drain, common source and common gate. And if you recollect, we also saw that we can actually bias the transistor to be in strong inversion, that is the normal saturation region, or in the weak inversion. So in which region do you get the maximum GM? Strong or the weak inversion? In weak inversion, we get a higher GM by ID ratio in weak inversion. But why do we generally prefer the strong inversion? Yeah, weak inversion, the usually sizes are very large because you want small VGS minus VT, and the currents are also small. So small currents with a larger parasitic capacitance kind of reduces the speed. So that's why we prefer to operate in strong inversion, typically for speed. So here common drain. So common drain is used as what typically? What is the use of a common drain typically? Voltage buffer. So what control source is it? This is the main use, voltage control, voltage source. Common gate, what we use it for? Current buffer, current control, current source. So this fellow is the only guy that gives us some gain. So this is our basic structure, right? And I mean, at this point you should be able to go back to your first practice set, and you should be able to find out all the small signal impedances by inspection at this stage, hopefully, right? All the small signal gains I asked you, all the small signal resistances, should hopefully be able to find it by inspection. So now, of course, this common source takes in one signal and amplifies it, but we wanted to amplify a difference between the two, so we decided to feed it like this. But here the issue was the impedance seen by V1 is large, but this is small. So we buffered this and fed it. That gave rise to the diffamp. So this was the first diffamp we saw. So again, this is a symmetric circuit. Anytime you have a symmetric circuit and you are given two different inputs, how do you analyze it? What is a simpler way to analyze? Yeah, so you have two different inputs. So what do you do to the two inputs? You decompose as common mode and differential mode part. So let's say it's differential mode part, VID by 2 minus VID by 2. In this case, how will the circuit simplify? Let's say, I mean, I decomposed as a differential part now. So what will happen to the circuit now? Yeah, if you have remember, if you have two linear networks which are symmetrical like this, all the nodes along the line of symmetry, they will be at 0 if the excitation is anti-symmetry. So this simplifies and gives rise to the differential mode half circuit. Similarly, if I apply a common mode signal plus VIC, then what will happen? How can you simplify this? I mean, not even line of symmetry. Every two nodes here, every corresponding nodes in the two half circuits, they will be at the same potential. So anytime I see two nodes with the same potential, what will I do? I go and connect it. So this again reduces the circuit to one half circuit. That lets you analyze it simply. So here, what is the small signal gain? Differential gain, by the way. I mean, if I draw the half circuit, I have this. I have VID by 2. This is ground. So what is the output by VID? Minus GMRD by 2. Okay. Now to increase the gain, we wanted to increase RD. So what did we decide to replace RD with? Yeah, PMOS, but in principle, what element would you put there? A current source, right? You want to have a large small signal resistance, so you put a current source. So that's what we did. but then we decided to generate the bias voltage and that we self bias this way. So this gave rise to the 5 transistor OTA. So one of the most popular circuits, we still use it for making single stage op amps. And here this is an asymmetric circuit, but what we observed was the following. As long as I provide a symmetric excitation, that is, if the gate voltages here are same, then what can you say about the drain voltages? They'll also be same. You can prove by contradiction. So these two voltages will be same. So that's how we can say that for operating point condition, these two are at the same potential, and the current also splits equally in the 2 branches. So here to find the small signal gain, we took the route of finding the short circuit current and the output resistance, because this is not purely symmetrical. Only for common mode inputs it is symmetrical. So for common mode excitations this can be simplified, but for differential mode you cannot simplify it completely. So you found the short circuit GM and R out. What is the short circuit GM here? GM of which transistor? Yeah, M1 or M2, both are same. And what is the output resistance? This is the output. R out 4 parallel R out 2. But again, just to remind you, it is not that looking up the resistance is R04, looking down it is R02. So in fact, if you do you remember what was the resistance looking down? 2 times R02, right? And to again explain it, so if you want to find the up and down resistance, the brute force phase is you break this node, right? Apply 2 test voltages, the same test voltage actually. Right? You find the current that flows up this way, and this ideally will have contribution to both the voltage sources. So if I call it VT1 and let's say I don't know VT this whatever. So the up current due to both the voltage sources that you calculate, that gives the up resistance. Similarly, you find the down current, and that will again in principle can have contribution due to both the voltage sources. That will help you find the down resistance, right? Cool. So now then to increase the gain of this fellow, what did we do? To increase the small signal gain of this, what did we do later? Yeah, we did Cascode. So again, I'll just do single-ended case. If I did Cascode, what was the looking resistance here? If I call it M2, M1, GM2, RO2, RO1, but to be exact, this is plus RO2 plus RO1. If the first term is larger, you ignore these two, but yeah, should be careful. And the another variant of Cascode we saw was the folded Cascode, wherein the main current source is say of one transistor NMOS, whereas the current buffer we use was of a different variety, a PMOS, or it could be the other way. You can use a PMOS here and NMOS here. And to increase the gain further, I can do cascoding like this continuously. But what was the downside if I keep doing cascoding? Yeah, remember that each transistor requires a minimum VDS. If I cascode more and more or stack more and more transistors, the minimum output voltage I can go here will be limited. So that is one problem. So we saw gain boosted cascode as an alternative technique. So again, the idea there was you have the normal cascode. So you make sure that the drain voltage here does not change a lot. So you actually give it to an amplifier. With respect to small signals, this is what was happening, and this was the gain boosted cascode. Now this was all nice and good, but then we realized that the gain does not remain constant versus frequency. Due to parasitic capacitance, it drops with frequency. So we looked at poles and zeros. So again, to summarize, poles is a characteristic property of a system. It doesn't depend on the input or what the output is, and the number of poles is the maximum number of independent state variables you can initialize. So I'll just say maximum number of independent state variables that can be initialized. Right. Whereas zeros, it depends on where you apply the input and where you take the output. Okay, And what was the technique we saw to see if we have zeros in the circuit or not? You short capacitor. So essentially, if you can short, let us say, 3 capacitors in your circuit simultaneously, and then you find that the output can be non-zero. How many zeros I have? 3 zeros. That's a general principle. I hope you got it. Now, finding the zero locations is a little bit easier. The idea is very simple. You assume that the output in the Laplace domain is 0 and apply KCL in your circuit normally, and then solve for the complex frequency S that gives you 0 location. But the poles is not very trivial. But there are a couple of cases where you can approximate the pole locations. So first is where you have uncoupled time constants or uncoupled poles. So where the ideas are following, let us say I have 3 capacitors like this in my circuit. If I find the resistance looking into one of the capacitor doesn't change, irrespective of whether I open or short the other capacitors, then I can say that this time constant is uncoupled from these two. So then let us say if I call C1, C2, C3. So then I can say that I have one pole exactly at 1 by tau 1, where tau 1 is C1 times R1. And R1 will not change depending on whether C2 is open or C2 is open, C3 is short, C3 is open, C2 is short, and all combinations. And the second case where we can do it was the following. If we can assume that the poles are all far apart, say P1 is smaller than P2, smaller than P3, and so on. And also the capacitances are also they are also in ascending order like this. Then we can kind of say that the dominant pole, the low frequency pole, might hopefully arise due to the largest capacitor. And for finding the resistance seen by C1, what do you do for these capacitors? You consider them to be open. So I'll say it's R1. Here you do C3, C2, everything to be 0. So here again the assumption is that the resistance seen by the largest capacitance is also very large. That way we can guarantee that C1 is also large, R1 is also large. So this will be the lowest frequency pole. So this assumption might be fine. So two things, of course this capacitance must be the largest. Also the resistance seen by that capacitance must also be the largest in your circuit. Now we can kind of extend it. So if I want to find the second pole, assuming that it is coming due to capacitor C2, here what will I do for C1? C1 I'll make it short. Other capacitors I can treat it to be open, and you will find R2. Similarly you can find this. But here again the thing to remember is only if R2, R3, etc. they are all of similar value, only then this assumption will be valid. See, for example, I can have a case where C2 is larger than C3, but if R2 is very small compared to R3, then you cannot say that P2 is smaller than P3. They can be close to each other, or it can be in the opposite direction also. So the inherent assumption we typically make is if the capacitances are all widely spaced apart, the corresponding resistances are all of similar value. So this we did, and then we saw that all our single stage OTAs were a first order system. And for a first order system, what is the unity gain frequency? If let us say the first order system is of the form A0 by 1 plus S by P1, what is the unity gain frequency? It is what? A0 times P1. And of course, if I use this fellow in a feedback loop with a feedback factor of beta, then the unity loop gain frequency is what? I'll say beta times omega. So under first order system, if I put it in negative feedback, was it stable or unstable? Stable. So then what was the need for going to multi-stage OTA? Yeah, as we saw, first order system or a single stage OTA, it has a very large output resistance to get a large gain. So the moment you put a small resistive load, it kind of gain goes for a toss. So that's why we decided to have a two-stage or multi-stage structure. And we started with the two-stage. So we actually do not know if this can be stable or not. And technically you should look at the closed loop poles and see if they are in the left half of S plane. But the proxy way we took is the following. We sketch the Bode plot and look at the phase margin. And if the phase margin is sufficiently larger, we say that it is stable. And we essentially saw two techniques to kind of make the closed loop system stable. One approach was to keep the open loop poles far apart. This, like as I say, keeping these naughty kids in a class, put one guy here, one guy there, so that they don't interact with each other and keep the class stable. Second is you let them sit close enough, but make sure that there is a strict adult sitting next to them so that they fall back in line. And the first was the Miller compensation, and second we did using feed forward. So let's summarize that quickly. So let me just do Miller first. So this is the first stage, GM1. So this is, let's say, G1 and C1. So this is GM2. Let us say I club all the conductances here and call it CL prime, GL prime and CL prime. So to compensate this, what did we do in Miller compensation? We put a capacitor across GM2 and can you quickly tell me the things? What is the DC gain here? Yeah, just to jog your memory so that you kind of remember, GM1 by G1 times GM2 by GL prime. And tell me the low frequency pole approximately. First give me the exact result, then you can simplify it. What is the total capacitance? I have C1 plus CC into 1 plus the second stage DC gain, and the conductance is G1. So practically this, in most cases, you can approximate as G1 by CC into GM2 by GL prime. And what is the high frequency pole? Again, first let's start with capacitance. Yeah, what is the total capacitance at the output? CL prime plus CC into C1 by CC plus C1. And what is the conductance? I have GL prime and a portion of GM2, and that fraction is CC by C1 plus CC times GM2. So this, if I assume that C1 is much smaller than CC and CL, C2 is smaller than CL, and GM2 is much greater than GL prime, then how can I approximate this as GM2 by CL? Okay. And in this case, what was the we had an RHP0, and where was the RHP0 located? GM2 by CC. Again, the idea is RHP0 is arising because we have two paths for the current. One path is from GM2, other is from CC. So it better be GM2 by CC. But to alleviate this or to remove this RHP0, what was one simple thing we can change here? We can put a resistor, and if I choose a resistor value RC to be exactly 1 by GM2, the RHP0 goes off. Right? And here, what is the unity gain frequency? Beta doesn't come because we're not looking at the loop. So what is the unity gain frequency? GM1? Okay, think of it this way. So now let us say this is the Bode plot. This is your omega u loop or omega u, right? So now let us say you are applying an input V in here. The current here will be GM1 times V in, correct? Now around the unity gain frequency, the transfer function goes as 1 by S. That's clear. So around this frequency, if I apply an input V in, the current is GMV in, but this current, where do you think will flow through? Flow through conductance or capacitance? My transfer function is of the form 1 by S, correct? I have a current GMV in. To get a transfer function of the form 1 by S, the current should flow through a resistor or a capacitor? Capacitor. So this is obviously going to flow through the capacitor, and CC is larger than C1. So typically all the current will try to flow here. Right? And again, let's say we are looking at sufficiently low frequencies where this guy is providing decent gain. So if this is providing good gain, what can you say about this voltage roughly, very approximately? We can approximate roughly as 0. Fine. This is just for a very qualitative explanation, not exactly, right? So now you see that, again let's ignore the 0 for now, I mean the resistor for now. So I have GM1 V in current flowing through capacitor CC, and this terminal is 0. So then what is V out? I have a current GM1 V in flowing through the capacitor CC. V out is the voltage drop across the capacitor in the polarity I have marked. So what is VO? Minus GM1 V in. So now what is the unity gain frequency? I mean V out by V in is minus GM1 by SEC, right? What is the unity gain frequency? Okay. So this is one way to look at the Miller compensation, where the main current transconnector is this fellow. This is trying to pump current through CC. And that's what happens. So the unity gain frequency is GM1 by CC. Okay. This is fine. Again, it's not exactly 0, this voltage, it's roughly 0. Don't take it exactly. So yeah. And here if I have to ensure good phase margin, what should I do to the poles and unity gain frequency? To increase the phase margin here, what will I do to the pole and unity gain frequency? I should make sure that my second pole is much greater than the unity gain frequency, right? So this is one way. This is Miller compensation, and we saw Ahuja as another technique to cancel the RHP0. That's fine. Then in the last class we looked at feed forward. So let's summarize that also. So let me first sketch this two-stage structure. So this is first stage, second stage. They'll call this GL prime, CL prime, G1, C1, GM1, GM2. So in the feed forward compensation, we wanted to introduce a left half plane 0. And how did we do that? By adding one more stage. And what was that stage doing? Yeah, so this was supposed to be a fast path, providing a quick and a dirty estimate, and that you accomplished by adding another transconductor. And the signs is this way. Again, you determine the sign based on whether you want the 0 to be in the left half plane or the right half plane. So this is what we did. Right? This was the feed forward compensation. So here again, what was the DC gain approximately? I mean, remember that at the heart of it we have a two-stage OTA. That's what we are trying to compensate. So what should be the DC gain? The DC gain of the two-stage structure. So this will be GM1 by G1 times GM2 by GL prime. Right? And where are the poles located here? Again, remember, for pole calculation you make the input 0. The moment input is nulled, GM1 is not active, GM3 is also not active, these two are not there. So you just have these two RC sections. They are coupled or not coupled? Not coupled. So what are the pole locations? G1 by C1 and GL prime by CL prime. Now we also have an LHP 0. And where is that 0 located? What was the location? Do you remember? Yeah, very good. GM1, GM2 by GM3 times C1. Again, the way you can quickly remember is, if you want to reduce the 0 frequency, you try to keep the slower path more slower, faster path more faster. So to keep the slower path slower, you reduce GM1, GM2, so that comes in the numerator. You also increase the capacitor, so it comes in the denominator. To increase the speed of the fast path, you just have to increase GM3, so that comes in the denominator. That's one quick way to remember. And what about the unity gain frequency here? again remember the unity gain frequency is characterizing the speed of your system. So the speed of the system is dictated by the slow path or the fast path. So in the fast path you just have a single stage OTA. For a single stage OTA, what is the omega u? GM3 by, is that okay? Single stage structure, DC gain times the first pole. DC gain is GM3 by GL prime. Pole is GL prime by CL prime. So GL prime cancel and you get with GM3 by CL prime. Okay. And here to get a good phase margin, what should I do here? I mean with respect to unity gain frequency, the 0 should be placed much before the omega u. Right? This is the thing to do here. Okay. And we also saw the main differences between feed forward and Miller. So yeah, this is fine.